We're going to continue with a second project on exoplanets. This one was mentored by BJ Fulton, who is a graduate student here. This one, I see BJ. Thank you again, BJ. This is your second time being a mentor, right, for High Star? At least, yeah. So he's working on his dissertation here on exoplanet searching. So his three student scientists are Joseph Kim, and Joseph, you're a returner, right? You went to the Mount Mini High Star last year? Okay. But if Joseph looks a little familiar, he had an older brother who was in the program for 2 years. So, yeah, this is not the reincarnation of Chris. This one is a little tall, this model's a little taller. Yeah, than Chris. Okay. So, yeah, his older brother went off to Yale, I think, right? Yes. Okay. I'm sorry, Emma Mroz, who is also here. This is another Maui team, so she's from Kihei Charter School. She'll be entering 9th grade, first time participant, right? And Son, were you first time? You were in the Maui Mini, so second time participant, Son Phan, from, also from Maui Mini, Maui High School, Son Phan. Okay, you guys ready? All right, take it away.
All right, cool. Welcome back, everyone. So as Mr. Nasser said, my name is Joseph Kim. On my left is Son Phan, and on the far left is Emma Mroz. And the title of our research project was Determining the Properties of Exoplanet HD 149026b using a combination of transit and radial velocity methods. So the previous group talked a little bit about the background information on exoplanets, but I'll kind of repeat it because you guys might have forgotten the information. So, an exoplanet, what is an exoplanet? It's a planet that orbits a star outside of our solar system. And how common are exoplanets in our universe? About a little more than 50% of the stars in our universe have one or more exoplanets orbiting around it, and different methods of detecting exoplanets are the transit photometry method, the radial velocity method, gravitational lensing method, and just direct imaging. So the objective, we wanted to find 6 different characteristics of exoplanets using a combination of transit photometry and radial velocity methods. So the first one we wanted to find was the radial velocity, and then the orbital period, and then mass, and then radius, and then density, and we wanted to predict the composition at the end.
So Joseph talked about how we're using the radial velocity method and the transit photometry method. Here we see the radial velocity method, which is a method that utilizes the Doppler effect to find small changes in the velocity of the star. So the Doppler effect is the property of waves to shift in wavelength when moving away or towards an object's perspective. So if an object is moving away, its wavelength will be stretched, therefore redshifted. And when an object is moving toward the observer, the wavelength is compressed, thus blue shifted. So we can use the Doppler effect with radial velocity because when an exoplanet orbits a star, the star also has a little bit of wobble in response to the exoplanet's orbit. So here we see one of the spectra that we collected. So this spectra is from the Keck telescope, which we took over 3 years, which is just random points. So from this spectra, we're able to find a wavelength shift, or a Doppler shift in this case. And we were able to plug that into this formula over here. This formula over here, where we were able to calculate a radial velocity. So taking that radial velocity, we were able to plot that on a radial velocity time series. And this radial velocity time series, we use the property of sine waves, the periodic property of sine waves, to find the period of the sine wave. So by using the periodic properties, we were able to find 2 similar points on the graph. Because it's a periodic property, you can find a period in between those 2 similar points. And we divided that distance of time elapsed by an integer number to make sure that there isn't several periods that are passing between that time. So we found that range of periods is 2.8 to 2.9 days.
So after narrowing down the orbital period to about a tenth of a day, we used a program to show all the intervals from 2.800 to 2.900 days. This was in order to find the closest chi-square statistic to 1, and we found the orbital period to be 2.8759 days.
So with that period that we found, we were able to plot the ray velocity versus phase. And here, like we said, is a clean sine graph. And from that sine graph, we were able to calculate the semi-amplitude to be about 40 plus or minus 2.9 meters per second. And from that semi-amplitude, we were able to plug that into this formula, which is beautiful. And we were able to rearrange this formula to solve for this value here, which is the mass of the planet. So from the mass of the planet, we were able to calculate a ratio, and given the mass of the star, we were able to multiply that ratio by take the mass of the star and divide it by that ratio to find the mass of exoplanet. And that mass happened to be 6.3 plus or minus 0.50 times 10 to the 26 kilograms, which is similar to the mass of Saturn.
So what Phan just talked about was all radial velocity method, and I'm going to be talking more about the transit photometry method. So a transit is an event where one celestial body crosses another one. So in our case, an exoplanet crossed a host star. So in this image right here, you can see when the exoplanet starts to go across the host star, and you see this light curve right here, there's a dip. So the lowest point would be the point where the exoplanet is right in the smack center of the host star. And the advantages of a transit photometry method is that it's very effective and sensitive, which means that a lot of exoplanets can be detected using this method. But some disadvantages to this is that for this to occur, a transit must occur, and a transit usually takes a very short time, or it lasts for a very short time. And some results produce a false positive result. So the light curve we plotted is right here. So we wanted to find the depth of the light curve, which is the distance from when the transit did not occur and the lowest dip part. So we averaged the flux of time before and after, and we averaged it, and we found the average flux when the dip was the lowest, and we subtracted it to find the distance, and we found also the error bars to it.
So here we constructed a formula based off of geometry, where we found the ratio between the radius of the host star and the radius of the target to the relative fluxes. And we found the radius of the target using this formula to be 6.8 plus or minus 0.40 times 10 to the 7th meters. And using the formula for the volume of sphere, we were able to find that the volume was 1.3 plus or minus 0.25 times 10 to the 24th meters cubed. So here we see this previous spectrum that we got. So the previous spectra that we got. And from detailed analysis of this detailed spectra, we were able to find that the mass of the star and the radius of the star, which you can see circled up here. And given that, we were able to find the mass of the exoplanet and the mass of the star based off the ratios we determined. And based off that, we were able to find the density of this exoplanet, which is 4.7 plus or minus 0.14 grams per centimeter cubed.
So we determined the composition of the exoplanet using the density from the exoplanet, which, as Phan said, which was the number that he said. And what we did was we took a percentage of element, and we took the density, and we figured out these by adding them up, the densities of these, and we found that for our hypothesis 1, we have 50% hydrogen, 20% of a metallic core, and 30% sodium. And so with this, we figured out these elements by comparing it to Saturn, since the density and mass of the star is fairly similar to this exoplanet, and the only difference is that it's extremely far away from our sun, Saturn, but however, this exoplanet is extremely hot because it's so close to its host star. And for our hypothesis 2, we have 45% hydrogen, 10% helium, 30% sodium, and a 15% hydrogen core.
So you might be wondering why we did all this research. So number one, we wanted to find we wanted to make sure that this transit method and radial velocity method worked, and our results did correspond with the current known density and all of these properties. And also we noticed that with a combination of the transit photometry method and the radial velocity method, we can find the density of an exoplanet, which we can kind of predict the composition with. And for future research, we hope to get more data points for this exoplanet to kind of shrink the error bars to get a more accurate answer. And next, we wanted to find a better method to predict the composition of exoplanets, because the density in an exoplanet is not uniform because there is a core, so yes. And also, we wanted to find a way to reduce the false positive results.
We would like to give a special thank you to our mentor, Mr. VJ Fulton. He was awesome. And our heads of High Star, Dr. J.D. Armstrong, Dr. Jeff Matthews, and Mr. Nasser. And as well as our amazing counselor, Michaela, she was amazing, and the Keck Observatory for their data from the telescope, which is where we got the data from our exoplanet, and the High Star students and staff. You guys were all amazing, and yeah. And then here's our image credits. And any questions or comments or concerns?
So why can't you guys accurately determine the planetary compositions?
This is because, as Joseph mentioned before, that the density of a planet itself is not uniform. So for example, it could be a very dense core with a very not dense atmosphere, or a medium dense core and a mediumly dense atmosphere.
Do you mean a mantle instead of
Yes, crust or not, yeah.
Oh, okay. Or for a gas giant, I guess.
Yes.
So would your results be consistent with this planet having the same composition as Saturn, since it has about the same mass as Saturn?
We can predict that it could have a similar composition, but like Emma also mentioned, the difference between Saturn and this planet is that this planet is much closer to its sun, therefore much hotter. And thus the states of the elements and the elements that can exist could be different.
As well as the fact that it's about 1,000 Kelvin or something like that, and it's extremely hot, so that sounds good.
Yes.
So you guys have both the advantage and disadvantage of awesome data and modeling. And so the question is, when you came up with those two particular models of what the chemical composition might be, what drove that for the hypothesis? What led you to consider those two specific hypotheses, or were there reasons why looking at those admixtures were particularly interesting to consider?
Well, as I mentioned earlier, I researched Saturn since it is close to there and other gas giant elements, and we compiled a table of solids, liquids, and gases of possible exoplanet materials or compositions of what the certain exoplanets are made of. And so we figured those would probably be a good fit considering how close it is to its sun, and the fact that those elements, it could be a gas giant since of how low the density of this particular exoplanet is, and it couldn't be a solid, mainly a solid, because solids are much more dense matter, and we figured a solid core, pretty much every planet has a solid core, so that would drive the metallic core, and as it resulting in being a gas giant.
But,
Oh yes.
yes. Just as a follow-up, So why is there the difference, for example, in helium being present there? That's one of the things that's different about the two.
Yes.
Why would it be interesting? Sorry.
It's okay. Well, we figured two different hypotheses will be great to show because we don't know exactly what they're made of. So it's great to have other means of trial and error, for example, and just to have an example of what it could be as a gas giant because we don't know for sure if it's just hypothesis 1 or just hypothesis 2.
Yeah, these hypotheses should fit the density about the same as the density that we found.
Okay.
Wait, also, we looked at common gases that are present in exoplanets. So hydrogen and helium were the most, so we wanted to put helium as one.
Okay.
Okay.
Okay, thanks.
Great. Let's thank our speakers one more time.